When we are talking about what chemists study, the composition, property, and transformations of matter, properties is what is dictated by composition and then lead to those transformations we have talked about throughout this entire semester. So what are the forces at play that help predict and dictate these properties? When we're trying to predict properties of a specific matter and knowing how it's going to interact with its surroundings, we need to understand the state of matter or the phase in which it is in, because that helps us understand the interactions occurring between those molecules and how much energy is bottled up within those compounds. Gases have interactions that are minimal because they have the most amount of energy, so they are moving around, and they may have instantaneous interactions if they collide and then move on, but there's nothing really keeping those particles together. Liquids have less energy and they're flowing, and with their flowing they're still passing each other, but they're going to have some stronger interactions between the separate molecules or particles, whereas solids are tightly packed particles that maximize the amount of interactions and create that kind of lattice structure. We're going to look at solids first and those interactions between the different types of solids, and then move our way through the different states of matter. The first structure we're going to look at are the ionic compounds, which we have talked about through the entire semester, but really starting to take a microscope and zoom in on what the structure is between these separate ions. As we've discussed, ionic compounds are made up of cations and anions, but it's not just one element. It's not just one sodium and one chlorine. It is a repeating structure, and they're held together by what is called intramolecular. So intra means within the same region. So this is the bond, and that bond is that electrostatic force between the positive and negative ions, and it just starts to repeat. So a salt crystal can be very large, and it's going to have untold amount of atoms, and it can get smaller and smaller as you dissolve or break it apart, but it's just a constant repeat of those ions. Now, in the solid state, it is very regimented in its lattice. So what happens to get it, or what needs to happen to get it to a liquid state? Well, here, because it's repeating ions, we need to disrupt that electrostatic force between the positive and negative charge to move it to that liquid state. Because it's a physical bond, well, the bond's not physical, but it's a high energy attraction, it takes a lot of energy to start to interrupt those electrostatic forces. So it's going to result in high melting points. So to go from a solid to liquid takes a lot of energy. For like sodium chloride, it's around 540 degrees Celsius, give or take, might be 580. But it's a lot of energy in order to start to separate those electrostatic forces for those ions to start to flow. And because it's going to have high melting points, it's going to have incredibly high boiling points to actually separate the ions into their gaseous state. So the strength of this solid is going to come from the attraction of that positive and that negative ion within that repeating state. Molecular solids. We're actually going to spend most of our time with molecular in the preceding or the next video because they are unique in the fact that they're not a repeating structure. They are a set molecule. There's a set, like the atoms, the ratio that is in that formula is literally the number of atoms that's in that molecule. So if we take a look at water, so water is H2O. So there's literally 2 hydrogens and 1 oxygen. So when you have separate water molecules, they have to be interacted by external forces. And those external forces are called intermolecular forces. So inter means between separate entities. So they've got the bonds between that hydrogen and that oxygen, but between 2 separate water molecules, you're going to have an outside force. Those are called intermolecular forces, which we'll talk about later. But because it's an external force, it's not a bond, it's not a strong interaction that is occurring, it's going to have weaker properties than that of, say, the ionic compounds. With this, so if we look at this bottom one with the CH4, we have these ionic compound, or sorry, these covalent compounds here, and they're just being attracted to each other by those weak intermolecular forces versus these strong electrostatic forces between actual ions. So depending on the size of the molecular compound, it has variable energy requirements to break those intermolecular forces to separate the molecules. So like water is a liquid at room temperature, whereas salts cannot be because of the strength of those intermolecular forces. Whereas sugar, glucose, C6H12O6, is a solid at room temperature because there's a lot more interactions that are occurring between separate solid molecules. An important piece to take away with molecular compounds in particular is when they change their phase, they're breaking those intermolecular forces. So it's an actual water molecule that they are separating. Whereas with this ionic structure, it is the ions that are separating within that lattice. And with the ionic solids, the only force we have to break is the bond itself, versus just an outside intermolecular forces with the molecular compounds. We have not talked about these next two at this point, but know that they do exist and they have their own unique properties. This next one is called network solids. Network solids is like ionic compounds where you have that repeating structure, but it's also like covalent where they are physically bonded. What it is it's a large number of atoms with similar electronegativity to each other. The most common network compounds are actually carbon-based. Diamond, which is the hardest substance in the world, is all, because it's all carbon, the bonds between those carbons, there's no overall pull between those the electrons within that bond, so there's no polarity. It's a complete even, and it's that repeating structure. It's incredibly strong. Carbon can also make graphite, which is what's in your pencils. And so the difference between a diamond is just this conglomerate of carbon atoms, whereas graphite is sheets. So the carbon interactions are lateral. And so when you're writing with a pencil, that is just sloughing off one layer of carbon at a time as you're using your graphite. There are two other types of network solids that are not pure carbon, that are silicone-based, but silicon is also in the same family as carbon, so it's going to have those same interactions. Silicon dioxide is what we use to make glass, or silica gel, stuff like that. It is equally as strong because of the interactions of how many bonds silicon and oxygen can have, so you can have that network being built. And we also have that carbon-silicon interactions, which makes that very lightweight kind of plastic that we can use on vehicles and whatnot. Because there's no unequal distribution of electrons or energy, the force or the strength of these bonds is incredibly high. So network solids have the highest strength of all the solids. They're going to have the highest melting and boiling points. These are the hardest to break. That takes the most energy to separate because those electrons are of equal distribution. So we have to get those electrons to move to either atoms to start to separate. And it's very, very hard to do that. One of my favorite is actually metals, some metallic compounds. So when we look at a metal, we have what happens is they form their cations. They're going to shed those valence electrons to have that positive charge. And so when that happens, you have these free floating electrons. And these free floating electrons are what we call delocalized electrons. They have the ability to be where they need to be to make the most stable product possible. So these electrons are going to move around the cations to make sure that the cations are being buffered and not being repelled from each other. And so depending on how many electrons there are being shed, so on and so forth. But this is what gives metals their unique properties. So we can bend metals very easily. They've got a lower melting point. And so what happens is when we melt it, we're going to separate those cations a little bit more from each other, and we're going to be able to mold and fold and do what we need. And when it cools, those cations are going to be stuck in place, but those electrons are there to buffer. And so then it's going to maintain that shape. So the fact that these free-flowing electrons allow the cations to be moved, manipulated, and shaped into whatever we have desire for those metals. Such a cool concept. It's not rigid and gives us the most flexibility. The last category is what we call amorphous solids. There's no regular arrangement, and a lot of times these are going to be solids that we make. They're not readily in nature, except for we can find some rubber type properties in nature. So crystalline is kind of what gets formed naturally as a state of matter. But due to a quick cooling of a substance, we can create amorphous solids. So amorphous solids can be like rubber, and that allows that flexibility. Glass is an amorphous solid, especially depending on how quickly that glass cools. That's what can give you the cool little like ribbons in glass art. But also over time, glass will deform as well. And then of course, plastics. And we allow a massive different rearrangement of atoms to allow that plastic to be molded and used. And so these amorphous solids, if we cool the solid really quickly, it's going to increase the amount of interactions within that force. And if it goes quick enough, it's not going to have time to go into its lattice structure, and it's going to be stuck in whatever format that it was cooled in, which gives us those unique shapes of those amorphous products.